If you're following along with the textbook, this is from section 5.2. But before, alright, here we have lecture 3.3, polynomial functions, which corresponds with section 5.2 from the textbook. So if you're following along with the textbook, this is from section 5.2. But before we begin our discussion on polynomials, we need to introduce power functions. Now, a power function is a function of the form written there. This is where a is a real constant and n is a positive integer, and x is, of course, the variable. So a power function means you just have a single powered variable. Now, power functions, they're smooth and continuous graphs, and they have a domain of all real numbers. Now, the degree of a power function is its exponent. So if it's x squared, that's degree 2. If it's x cubed, that'd be degree 3. And if it were x to the 7th, that'd be degree 7. Now, we can actually determine the shape of a power function simply by identifying its degree and the sign of its leading coefficient. So, for example, if you have a power function that has an even exponent and it's a positive coefficient out front, it's going to look like a parabola. If it's still an even degree and negative out front, then it's just going to be a parabola but opening downwards. And we saw that in the last section with quadratic functions. So even degree positive means both tails are going up. Even degree negative implies both tails are going down. Now, if you have odd degree, like a cubic or fifth degree power function or something to that effect, the tails will be going in opposite directions. So if it's positive and odd degree, it'll start by left tail going down and right tail going up. In other words, you have a net increase going on. And if it's negative, you will have a net decrease going on. So what do I mean by a net decrease? It's going to start high and end low. So that's how the graphs will look. So let's go ahead and look at some examples. So here we want to determine if the function is a power function, and if so, sketch its graph. So number 1, this is a power function. Notice it is a 6th degree power function, looking at the exponent there. So that means it's even degree and negative up front. So that graph will look something like this, like a parabola opening down. Now note that example 2 is not a power function. Notice the x is in the exponent's place. If the variable is in the exponent's place, it is an exponential function, something we'll be discussing in the next unit. So this is not a power function. It's not the correct structure. Number 3 is a power function, and it's 8th degree. And notice it's positive out front. So positive and even means the graph will look something like that. Now that brings us to polynomials. Now that we got power functions out of the way, we can discuss polynomials. Now basically a polynomial function is just a bunch of power functions added and subtracted together. So if we combine a bunch of power functions, we get what's called a polynomial. So polynomials is a bunch of power functions strung together. And the graph of the polynomial is still going to be smooth, continuous, and have a domain of all real numbers. Now the degree of a polynomial is given by the degree of the leading term. Or in other words, the dominant power function in there. So the degree is given by the dominant power function in the polynomial. But before we discuss that, let's look at some graphs here. So I really want to stress smooth and continuous. Polynomial is smooth, meaning there's no janky bits, no sharp corners you can cut yourself on. Nice, smooth, rolling curves. And it's continuous, meaning it's all one single piece. So example 1 is representative of what we can expect to see from a polynomial. Example 2 is not. Note that it has, sharp corners. That's not smooth. It has cusps. Those are not smooth. And it has gaps in the graph. So it's definitely not continuous. So that is not a polynomial. And that idea of smoothness will be absolutely crucial when you move into calculus. So let's look at some examples here, just to get used to determining leading. Now the leading term is basically the dominant power function. Now what do I mean by the dominant power function within the polynomial? It's the power function with the biggest degree. So if we look at function g here, in example 1, we can see the biggest degree is 7. So the leading term is basically the dominant power function, which is 3x to the 7th. And the degree is going to be the degree of that corresponding power function, which is 7. So the leading term, now number 2, I should have read the directions. The directions state, determine if it is a polynomial. If so, determine the leading term in degree. Number 2 is not a polynomial. Notice we got variables in the denominator, so that means it's automatically not a polynomial. You got variables inside of a radical, that's not a polynomial. And you got variables raised to a negative exponent, which basically puts variables in the denominator, therefore not a polynomial. Now number 3 is a polynomial. If we want, we can actually multiply this out. So let's go ahead and multiply this out. We got x minus 1 squared, which is x minus 1 times x minus 1. So when we multiply that out, that gets us x squared minus 2x plus 1, and then distribute accordingly. We get negative 2x to the 4th plus 4x cubed minus 2x squared. So in this example, our leading term is negative 2x to the 4th, and thus our degree is 4. Now, what we had in example 3 was a polynomial. It's just been factored. So if we want to multiply it out and write it in descending order, we can. And if we put it in descending order, we'll see that dominant power function in front. That's why it's also known as the leading term, because it's leading in front when you put it in descending order. Now, if you look at number 4, this is a polynomial. Notice there's no variables in the denominator, no radicals, no rational exponents, no funny business. If you multiply all of this out in example 4, you would get something that looks like a standard polynomial. But you can tell just by looking at that, multiplying it all out is going to be extremely tedious, and it's not necessary. So we don't have to multiply everything out. We just got to multiply the leading bits, so to speak. So if we multiply the leading bit in the first factor, which is 7, then you have times x squared, then x to the 5th, and then the next factor we have times 2x. So we multiply all that and we get 14x, so 5, 6, 7, 8 when we multiply all that. So that tells us the degree is 8. So here we have an 8th degree polynomial. So you don't have to multiply out the entire expression to figure out the degree, or to figure out the leading term. Now that leading term is going to be crucial in describing the end behavior, or I should say in determining the end behavior. And that's because for large values of x, the graph of a polynomial is going to be behaving like the graph of that dominant power function. So if you recall, even and positive, we already discussed this a few minutes ago, means the two tails are going up. Now I stress the end part in end behavior. We don't know what's going on in the middle, or we don't know what's going on in between the two tails, but we do know that as x gets very large, the two tails will be going up because it's even and positive. For even and negative, it would have the end behavior of a parabola opening down. Again, we don't know what's going on in the middle, but we know as we move out, it would have the end behavior of a parabola opening down. Again, we don't know what's going on in the middle, but we know as we move out, it's going to be like a upside down parabola, i.e. both tails are going down. Now if it's positive and odd degree, it's going to be a net increase and tails are going opposite directions. So you're going to start low and end high. And it's just going to be the reverse of that for odd and negative. So let's go ahead and practice this. Let's describe the end behavior of number 1. So the leading term is negative 2x cubed. notice that this is negative and odd degree. Alright, negative and odd means it's going to be a net decrease with tails going in opposite directions, so it's going to start high and end low. And then let's go ahead and look at example 2. Leading term is going to be 1/2 times x squared times x to the 4th. When simplified, is going to be 1/2 x to the 6th. So notice this is positive out front and even degree, 6th degree. So as x goes to negative infinity, it'll be increasing, and as x goes to positive infinity, it'll be increasing. In other words, both tails are going up. And we'll come back to this end behavior. It'll be crucial when we start graphing these. And before I move on, just briefly discussing end behavior. If I make up some random polynomial like 2x to the 7th minus 3x to the 4th plus 2, well, we know the dominant term, the dominant power function inside this polynomial is the 2x to the 7th. Now, for small numbers, x to the 7th and x to the 4th aren't that different, so to speak. 1 to the 7th is going to be the same thing as 1 to the 4th. 1.1 to the 7th isn't going to be too far from 1.1 to the 4th. But as x gets larger and larger and larger, then this term is going to really pull ahead of the others. Right? 10 to the 7th is a much bigger number than, say, 10 to the 4th. Same thing with 100 to the 7th. Right? If you take 10 to the 7th, that's going to be 7 zeros. 5, 6, 7. And 10 to the 4th is 4 zeros. Right? You're comparing 10,000 to 10 million. So in other words, as x gets large, all the other terms become insignificant in comparison. Right? The leading term is just going to completely eclipse the lower degree terms. So that's why we see that type of behavior out at the ends. Now, the end behavior tells us what's going on at the ends, but to figure out what's going on in the middle, so to speak, that's where we really want to focus on zeros, or the roots of a polynomial. So if f is a function and r is a real number for which f at r equals 0, then that r value is called a real zero function of f. Now, r is a real zero of f. Another word we use is a real root, or root of f. It's a x-intercept, right? So all real zeros are also x-intercepts. X minus r is a factor of f. That's going to be very important. Same thing with the x-intercept. And this is a little redundant, but r is a solution of setting the polynomial equal to 0 and solving. But it's really that factoring property that's key. So write a polynomial of degree 7 whose zeros are negative 3, 2, and 5. So in order to have a 0 of negative 3, I have to have a factor of x plus 3. That way when I set x to negative 3, you get 0. If I want a 0 of 2, I need a factor of x minus 2. That way when I plug in 2, I get 2 minus 2, which is 0. So you can see why these are called real zeros of the polynomial. If I want a 0 of 5, I need to have a factor of x minus 5. So we got the 3 requested zeros, but it also wants degree 7. Well, this is degree 3, so how can I get it to degree 7? Okay, there we go. Now it's degree 7. Because if you were to multiply it all out, you'd have x to the 7th. Now there's multiple correct answers. I could have also done this. Make that degree 2, make that degree 2, and then make this degree 3. That way it adds up to 7, and so on. There are more possibilities here. Now, here we move on to the multiplicity of a 0. And the multiplicity of a 0 is essentially its power. And this is very, very important. If it has even multiplicity, it will bounce. If it has odd multiplicity, it will go through at that point. So this is going to be crucial for graphing and understanding the visual perspective. So here let's go ahead and determine the zeros. Now the zeros are the same thing as the x-intercepts. So for this example, we have a 0 at 2. This has a multiplicity of 2, which means, a multiplicity of 1. Now, if you look at the exponent, it's power 1, so it's multiplicity 1. So visually that means it'll go through. And then we have another x-intercept at -3. Now if we look at the exponent there, look up at the polynomial, you can see it has an exponent of 2, so that we see that's multiplicity 2. Even multiplicity means it will bounce. More on that later. And then we have another x-intercept at 1/2. This has a multiplicity of 4, looking at that exponent, which is even, so it will bounce. Now for number 2, what we're going to have to do is we're going to have to factor that. So notice all terms have a common factor of x cubed, so let's factor that out. And then we can factor that trinomial in there. So that will factor to x plus 4 and x plus 2. Alright, so we're now ready to determine the x-intercepts, or what is known as the real zeros of the polynomial. The first one is at 0, and that has a multiplicity of 3 because it's x cubed, so that means odd. It's going to go through. The next one is at -4. It has a multiplicity of 1. There's just one of them in there, so it's going to go through. And then at -2, that also has a multiplicity of 1, which means it's going to go through. Now, turning points. If f is a nth degree polynomial, it can have at most n minus 1 turning points. So, basically, if I have a 4th degree polynomial and some stuff there in the middle, that means its graph can have at most 3 turning points. Now this doesn't mean it will have 3 turning points. It just means it can have at most 3 turning points. It could have 2 turning points. It could have 1 turning point. But it cannot have more than 3. Right, so this graph I could have, say, 1 turning point, 2 turning points, 3 turning points. And I can't have any more than that. So that's a turning point, that's a turning point, that's a turning point. So in other words, a 4th degree polynomial can have at most 3 turning points. A 7th degree polynomial could have at most 6 turning points. A 100th degree polynomial could have at most 99 turning points. So in other words, if you want more squiggles, you need a higher degree. Alright, so let's take everything we've discussed and tie it all together. So we're going to take end behavior, we're going to take intercepts, we're going to take turning points, we're going to tie them all together. Now, let's begin with this example. And it asks us to find the leading term. So we just multiply the leading bit. So that's x times x cubed times x squared, which gets us x to the 6. Notice that that is positive and even, so both tails are going up. If you need to pause and go back to that chart earlier, I'm just referencing that chart. And then you got y-intercepts. We're doing those on the second exam. You set x to 0 and solve accordingly. So we have y equals 0 times 0 plus 2 cubed times 0 minus 5 squared, which equals 0. So we have a y-intercept at 0. X-intercepts, we have everything factored. So we have 0, which is multiplicity 1, so it's going to go through. We have -2. Now if you look at that -2, it has a multiplicity of 3, which is odd, so it's going to go through. Then we have another one at 5. Notice it has a multiplicity of 2. It's just even, so it's going to bounce. And notice it's degree 6, so you can have at most 5 turning points. So let's go ahead and take all of this together and graph it. So let's mark our intercepts. Got an x-intercept at 0, and it goes through, so I'll put a little tiny t there for go through. Another one at -2. where it also goes through, so I'll put a little tiny T there. And another one at 5. I'll put a little tiny B there as in Bravo because that's where it bounces. So, now I'm going to look at the end behavior, and I'm going to go from left to right. So my end behavior tells me I'm going to start up high, and then I'm just going to weave it through my intercepts. So I'm going to go to the first intercept, and I'm going to go through. Now I have to turn around to go to the next intercept, and I'm going to go through. And then I've got to turn around to get to the next intercept, and notice it says bounce, so when I get there I'm going to bounce off. Now there's no more intercept, so I just continue on in this direction. And notice this matches up with the described end behavior. Now, some of you may be wondering, well, how do we figure out the turning points? Well, if you want to know exactly where the turning points are, take Calculus 1. Well, we discuss how to find those local extrema in Calculus 1. But for now, in college algebra, I just really want to focus on intercepts and multiplicity and end behavior. And we can get more detailed when we have calculus in our toolbox. But for now, this is sufficient detail. So if another person's graph looks like this, where they went way down here and maybe didn't go as high, then bounced, that's perfectly fine. Let's look at number 2. Figure out our leading term. So we have negative 1/9 times x squared times x to the first. So we get negative 1/9 x cubed. Notice it's negative and odd. So negative, odd. Odd means the tails are going to be going opposite directions. Negative means net decrease. All right, so I'm going to start high, end low. So there's our end behavior. Now the x-intercepts, we got everything factored, so we got a factor of real 0 at 3. Notice it has an even power corresponding to that factor, so that tells us it's going to bounce like a little tiny parabola there. Got another x-intercept at negative 4. Notice it's multiplicity 1, or power 1 there, so it's going to behave a little bit like a line would and just punch on through. And then for our y-intercepts, we set the x value to 0. And if you want, you can just type that into your calculator, and we get negative 4. So there's our y-intercept. And note this is degree 3, so we can have at most 2 turning points. Alright, so let's go ahead and mark our intercepts. We got an x-intercept at 3 where it's going to bounce. Put a little tiny b there just to remind myself when I go to sketch the graph. Got another x-intercept at negative 4. I'm going to put a little tiny tango there just to remind my future self to go through there. And then I got a y-intercept at negative 4, so I'll make sure I hit that too. Now when it comes to y-intercepts, it's a function, therefore there is no multiplicity to be concerned with. Now we need to look at our end behavior. So the end behavior tells me I'm going to start high. So I'm going to start high and start weaving through my intercepts. So I'm going to go through here. I got to turn around, or I got to hit this y-intercept, get to my next intercept, and it says B's in bounce. So I got to go ahead and bounce off that. There's no more x-intercept, so I continue on in that direction. Now notice, if your multiplicity is correct, and you started in the correct quadrant, then your end behavior, you can use your end behavior to check your answer. For example, I know with my end behavior, the right-hand tail needs to be going down. So I know that I'm correct, or I have it's good evidence that I'm correct because that's what my graph displays. If your tail were going up, then that means you probably missed an x-intercept, or you accidentally went through when you should have bounced, or you accidentally bounced when you should have gone through, or something to that effect. Let's do one more graphing example. Looking at number 3. Now what makes this a little more difficult is we're going to have to factor it. So these, we can factor out a negative and an x squared. So we get x squared plus 3x plus 4. And then that factors the x, that should be minus 4. So it'll factor to x plus 4, x minus 1. So our leading term is negative x fourth. We can see that at the very original expression before we factored. Notice it's negative and even. Even degree tells us the tails are going in the same direction. Negative means both down. So there's our end behavior. We got an x-intercept going from left to right at 0, and it's x squared, so 0 squared. It's even multiplicity, so it's going to be a bounce there. Another x-intercept at negative 4, which is, if you look at that factor, it's power 1, or it's one of those factors, so odd multiplicity means it goes through. Then the next one is at 1, and that's also raised to the first power, or odd multiplicity, so it's going to go through. If we plug in 0 for x, we get 0 for y. And since it's fourth degree, we can have at most 3 turning points. Alright, let's go ahead and sketch the graph. So let's mark our intercepts. We got an x-intercept at 0, where it's going to bounce. Put a little tiny b there. Got an x-intercept at negative 4. It's going to go through. Another x-intercept at 1, where it's going to go through. And if we look at our end behavior, we're going to start down here. The left tail starts going down, and we're ready. So we're going to go through. Turn around. And then we're going to bounce. And then we're going to go through. And there's our graph. Looks something like that. Excellent. Now let's try the reverse. We've been going from the function to the graph. Let's see if we can go to the graph to a potential function. So, let's look at example 1 here. Write a possible function for the given graph. So, we don't know what the leading coefficient is. That will be the last thing we do, so we'll just call it a for now. Now notice we got an x-intercept at negative 2, reading from left to right. An x-intercept at negative 2 means we have a factor at x plus 2. Now notice that it's a bounce, which means it's going to be even power. And then we got our next intercept at 3, which means we have a factor of x minus 3. Now notice here it goes through, so it's just going to be odd power. We'll just leave it at 1. And all we got to do now is, now I'm going to plug in a point. I'll plug in the y-intercept and solve for a, just like you were doing in your last homework assignment that you guys already turned in. So we got a point, y-intercept at 0, negative 3. So I know the y-coordinate is negative 3 when the x-coordinate is 0. So we're going to go ahead and solve that. So that's going to be negative 2 squared is 4 times negative 3 is negative 12. Just like that. And then when we divide, we get 3/12, which reduces to 1/4. So we know for this graph, to hit that y-intercept, the alpha value will be 1/4. So there's a possible function for the given graph. Alright, let's try one more. So the leading coefficient is the last thing we will figure out, so we'll just call it a for now, and start doing our x-intercept. So going from left to right, we got an x-intercept at negative 3, which means a factor of x plus 3. Now notice it bounces, so we'll give it an even power. Our next intercept is at positive 2, which means a factor of x minus 2. Notice it goes through, so we'll leave it as is. And the next intercept is at 5, so we have a factor of x minus 5. Notice it goes through, so we'll leave it as is. And then we go ahead and plug in a point. So let's go ahead and plug in a point and solve for a. You can plug in any point you want off the graph so long as it's not one of the intercepts. The intercepts will zero out everything. So plug in any point you want so long as it's not an intercept. Let me rephrase that. You can plug in any point you want so long as it's not a x-intercept. If you plug in a x-intercept, it will zero out the function. We can go ahead and plug in a y-intercept. So we have a y-intercept at 0, 2. So I know the y value is 2 when the x value is 0. And we'll go ahead and solve that. The y-intercept makes these equations very easy to solve. So we got a times 3 squared, which is 9, times negative 2 times negative 5. So you multiply all that, we get 90 times alpha. So alpha is 2 divided by 90, which is 1/45 when you reduce. So our equation is 1/45 times x plus 3, quantity squared, x minus 2, x minus 5. Bada bing, bada boom. There we have it. And there we go. We are done with polynomials. So guys, we're 75% done with Unit 3. If you want, you can go ahead and start working on that test review, and just or move on to the rational functions, whichever strikes your fancy. Keep up the excellent work and have a wonderful day.